How do you design a GPU cluster for AI training? Designing a GPU cluster is like building a high-speed logistics network for a massive factory. You start by calculating the weight of the work, the model's parameters, batch size, optimizer state, and precision. These decide the memory and compute footprint. Large models, like a 70 billion parameter LLM, can require hundreds of gigabytes of gradient traffic every second. So you next design how GPUs communicate. NVLink and InfiniBand act like dedicated rail lines that must move gradients faster than GPUs generate them. If compute outpaces communication, training stalls. After that, you engineer storage so the dataset feeds the GPUs without pause, the way raw materials must reach an assembly line right on time. Finally, you add cooling, redundant power, and checkpointing so long jobs survive hardware failures. Interviewers love hearing, start with model math, then size compute, network, storage, and reliability around actual throughput needs. Once you imagine the cluster as a coordinated supply chain, the whole design becomes far easier to reason about. Core components of GPU cluster architecture. A GPU cluster works only when every layer supports the others, almost like a well-run hospital where surgeons, labs, transport, and power backup stay in sync. The compute layer is the operating room. GPUs like the A100 or H100 perform the core operations while CPUs prepare batches and handle data decoding. The network fabric is dedicated patient transport, using 400 gigabytes InfiniBand or NVLink to move gradients between nodes with minimal delay. Even one congested link can slow a training job by half. Storage is the diagnostics lab, often using Lustre, GPFS, or NVMe tiers to deliver large data sets and all the rapid checkpoints. Cooling, airflow, and redundant power keep everything stable during high load periods. Interviewers often ask what matters most. The best answer is balance, because an imbalanced cluster forces top-tier GPUs to wait on weaker layers. When you see a cluster as a living ecosystem rather than a pile of servers, its design becomes far easier to understand. Design workflow, from requirements to deployment. Designing a cluster follows a clean engineering workflow. First, you measure the model's true needs. Parameters, batch size, and precision determine memory, compute, and communication volume, much like checking the load before choosing a vehicle's chassis. Next, you choose a network topology, such as fat tree or dragonfly. These designs reduce hop count and avoid oversubscription, which is essential because all reduce behaves like every GPU passing notes to every other GPU at the same time. Then, you configure distributed training. Data parallelism is like giving each chef a full copy of the recipe. Tensor parallelism is like splitting a single recipe across many chefs. Pipeline parallelism is like arranging chefs in stages on an assembly line. Tools like NCCL, Orevod, and PyTorch DDP coordinate the flow of these gradients and activations. Finally, schedulers like Slurm or Kubernetes deploy jobs and monitor GPS utilization, network congestion, and I/O throughput. Once you follow this sequence, cluster design becomes methodical and predictable. Well, common follow-up questions. GPU memory limits are one of the first issues teams hit. Techniques like gradient checkpointing or mixed precision compress activations, the way you might shrink a long movie so it fits on a smaller drive. Model, tensor, or pipeline parallelism divide huge networks across GPUs, just like assembly stations split a complex product into manageable steps. When bandwidth comes up, remember the numbers. Training a large LLM can push more than 300 GB per second of gradient traffic across interconnects. If the network can't handle that, GPUs show 50 to 70% idle time in profiling tools. Fault tolerance often uses automatic checkpoints in node health monitoring, similar to autosave in a game that protects hours of progress. Cost optimization usually means reducing idle GPUs, tuning batch sizes, improving data pipelines, or using preemptible nodes. Scaling questions are common. The clear answer is that scaling flattens because communication, I/O, and synchronization grow with every additional GPU. Even top research labs face the same constraints. Real-world cluster architecture. In real clusters, the training pipeline feels like a synchronized production line. Distributed storage holds the dataset, and CPU workers process samples like sous chefs preparing ingredients before the head chef takes over. High-speed loaders then feed GPUs at several gigabytes per second, because even a short pause can starve a GPU and waste expensive compute time. The forward pass runs in parallel across all GPUs. During gradient synchronization, all reduce acts like a round table, where every participant shares updates and agrees on a unified result. The backward pass then updates weights consistently so every GPU remains aligned. In interviews, the strongest answer to where do real clusters break is most failures start in I/O or pre-processing, not in the GPUs themselves. Real labs like OpenAI and DeepMind scale data pipelines as aggressively as compute because modern training loops demand multi-gigabyte per second throughput per GPU. Once you picture this as a precise production chain, the whole system becomes much more intuitive. Great job learning today. If this helped you feel clearer or more confident for your AI or ML interviews, tap like so more learners can find you. If you want simple guidance for every interview topic, subscribe so you never miss the next lesson. You can share your questions in the comments. I read them, and they help me choose what to teach next. And if you know someone preparing for interviews, feel free to share this with them. Keep going. You're improving with every step. I'm here to help you grow.